Hello, everyone. I'd like to thank Dr. Mendez for giving his tonight for us. I'd also like to thank Marshall University, the College of Science, and the Physics Department. They've always been very supportive of the things that SPS does and the outreach and the activities. I'd also like to thank the American Institute of Physics. Their help to sponsor this event. So thank you to them. And we are also covering some of the costs with our local chapter here of Society of Physics Students. So I'd also like to thank Jackie Sizemore and Ellie White. They've done a fantastic job of organizing this speaker series. I believe we started this in November of last semester, and this is going to continue on for quite a few months. We've got some great speakers lined up. Dr. Tanner's talk is coming up next month. That's on March 17th, I believe. And same time, 7 p.m. And come check us out for all these other talks that we're going to have. We're going to have one per month, and it's going to be the same format as this one. So if you're interested in physics or interested in some of the things that you hear tonight, come check us out in the physics department at Marshall. We have 10 faculties, 6 of them are active in research. We have research from condensed matter physics rather, and all the way to water filtration. So we have a broad spectrum of research that students can go into. Marshall has about 9,400 undergraduate students and 2,800 graduate students. It is a doctoral university. We have a BS program in physics as well as a master's degree in physics, if that interests you. And we have 5 areas of emphasis for the physics track. So if you're interested in chemistry and physics, we have a track for that. Applied physics, which has some engineering in it, the pure physics track, biophysics, as well as a medical physics track, which helps propel you for studying to pass your MCATs if you're interested in medicine. So those are our areas of interest. If you have any questions for me about the physics department here at Marshall University, you can just shoot me an email. That's my last name, McBride, McBride, and then s@marshall.edu. And I'd be happy to talk with you or your parents about any questions you would have about starting a student career in physics here at Marshall University. So I think with that, I'm going to hand it off to Ellie, who will introduce Dr. Mendez. And I thank you again, Dr. Mendez, for being flexible on the schedule here with all of our wonderful weather that we've had recently. So I do appreciate you working with us on that.
Yeah, so thank you so much, Dr. McBride. And thanks so much to everybody for coming out tonight to what will be the 4th talk in our Faces of Physics series. So I am really excited to learn more about habitable exoplanets from astronomer and astrobiology expert, Professor Abel Méndez, as I'm sure all of you are. And I'm eager to introduce him really shortly. So after the presentation, just like previous times, if you were here, you'll remember we will have a live Q&A at the end, and we welcome you to share your questions via the YouTube live chat, or you can post your questions on Twitter by tagging us at MU Physics Club. If you enjoy this talk, as Dr. McBride mentioned, we hope you'll join us for future installments of the series. Dr. Candace Tanner of the National Cancer Institute will be joining us at 7 p.m. on March 17th, St. Patrick's Day, to talk about the physics of cancer. And West Virginia University researcher and radio astronomy expert Pranav Sanghavi will be speaking with us in April. And the topic will be announced soon. And more speakers will be advertised soon as well. So if you'd like to receive email updates about upcoming events, we'll be sharing a link in the chat where you can go to sign up. So now it's my absolute honor to introduce Professor Abel Méndez, who is a planetary astrobiologist and director of the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo. His research focuses on the habitability of Earth, the solar system, and extrasolar planets. Professor Méndez is a NASA MIRS Fellow with, hopefully I said that right, MIRS Fellow with Physics and Astrophysics Research experience at Fermilab, NASA Goddard, NASA Ames, and Arecibo Observatory. So some of you may have heard of the tragic collapse that was suffered by the world-famous Arecibo telescope that's located at the observatory over the winter, which is an extremely sad thing for astronomy. And of course, we send our thoughts to everyone who works there. And to Dr. Mendez, and hope that another telescope can be built in its place at this really incredible facility. So it's a huge loss. Professor Mendez we're really lucky to have him here. He's best known for developing the Earth Similarity Index, the visible Paleo-Earth project, and maintaining the Habitable Exoplanets Catalog, a database of potentially habitable worlds. He is also co-author of the popular science book Searching for Habitable Worlds, which I just read, and I highly recommend it. His research has been highlighted by many international publications such as National Geographic, Scientific American, and Discover magazine. Professor Mendez is currently working on theoretical models of the suitability for life of planetary environments, the characterization and detection of potentially habitable exoplanets, and the observation of radio emissions of red dwarf stars from the Arecibo Observatory. He's really active on Twitter, sharing astrobiology news as at Prof. Abel Méndez. And we can share that in the chat as well. Shares lots of really great things on his Twitter. So without further ado, I'm going to turn things over to him right now so we can get started. So thanks again to all of you for coming, and extra special thanks to Dr. Mendez for making the time to talk about his work with us today in the midst of his very busy schedule. So thank you.
Thank you for having me, especially to you, Ellie. It's my pleasure to talk to you about a little bit about the things we do at Arecibo. And when I say Arecibo, there's two things. There's the observatory and there's my university campus of the University of Puerto Rico. We have a lab of planetary habitability. We study the theory, but we also use the Arecibo Observatory for studying stars with potentially habitable planets. So we do theory and experimental work on habitability. And today I will focus in some interesting general results plus some specific results that I will be sharing during this week in particular. There is the Habitable Worlds Conference going on through the week. So we have been a little bit busy about this topic. And let me start for some basic things that we need to understand about habitability. Here's some common assumptions about habitability and exoplanets. First, that we cannot define habitability, but this is a well-defined concept in biology since at least the last 40 years. So there has been a lot of disconnection between what astronomers want to do now and what we know from biology. I am a physics and astronomy by training, but I had to study a lot of biology to go into this field. Another thing is that is impossible to quantify exoplanet habitability because we don't know enough information about this world, which is true. But you don't need all information to assess habitability. And the thing is that when you're thinking habitability, you just want to think, you're thinking of everything. And the idea is you just want to do a analysis by parts. For example, weight, how these specific variables affect the habitability of your system. So it's not that you need to consider all variables to learn something novel, the habitability of the different environment. Finally, that any habitability model pretends to determine if planets are habitable or not. And that's a oversimplification and impossible task. We don't do that even for Earth. We are not interested in if the thing is habitable or not. And that's our wish. So the main purpose of habitability models is just to weight how the environmental factors, the variables there, affect the system. But it's not necessary to say that a system is habitable or not. But we need to go a little bit further to understand that. And here, there's this type of environments. We know that terrestrial ones are habitable. And we presume that the planetary ones like Mars here, the Moon and Venus are not habitable. The only way to determine if any of these places are habitable in the common sense is finding or putting life on them. So that's the only way for sure to know if these places are habitable or not. which is observable here in the picture, that at least for dry forest and the rainforest, you see this habitable in that sense. So since habitability models are not life detection instruments, although they might provide some guidance, their purpose instead is to understand why the difference here. So it's more a bigger question. It's not that is this habitable or not, but looking pictures here and why is the difference, the transition, let's say for the case of the habitable Earth, why the transition from rainforests to deserts? What factors are changing this environment to move from one condition to the other? And even if we look at the moon, Mars, and Venus, and we could say they are not habitable, but I want to know more. How different are they? How less habitable in this case? Which one is worse? So that's our valid questions that habitable models are designed to answer. So the binary habitable, not habitable problem is an oversimplification of what habitability models do, leading to misinterpretation of the application and usefulness. Let's simplify habitability. First, the biology definition. Habitability is the suitability for life on an environment, as simple as that. And it grows in complexity when you go into details. But for simplicity, what we need for a habitable environment, we can use the analogy of the classical elements, air, water, earth, and fire, because that's exactly what we need for an habitable environment. More formally, we need a gas phase, an atmosphere. We need a liquid phase, a hydrosphere. We need a solid phase, a lithosphere, and some energy source which could be light or chemical energy. And the reason we need the three phases is because at least the five basic elements necessary for DNA, the basic structure of life, are not in only one phase. You have, for example, that for air, you can have hydrogen, carbon dioxide, nitrogen, oxygen. You have water here with hydrogen and oxygen. But phosphorus in particular is usually only in the lithosphere. And so you need an environment that provides all these ingredients in a lot of quantities and that they can be mixed. So it forces you to have the three states of matter plus some energy. And if you consider the rest of the chemical ingredients necessary for life, then you will be more convinced that you need the three phases. So let's apply this simple analogy to understand life on Earth. So when we have a rainforest, we have this, here I show you icons of air, water, earth, and energy. So in the rainforest, you have these four elements in abundance, and that's why you have life there present that is visible to your eye. And that provides the energy for complex life, like animals. And it drives a large biosphere. But it is amazing that in a planet so habitable like Earth, we have things like this. Dry deserts. So this is a picture. And we, at least in our eyes, we don't see life there. And the limiting factor here is water precipitation. You don't have enough water in the worst dry deserts, and there's always life, microbial life, because it needs a little bit amount of all these ingredients. But for complex life, multicellular life, then you need a lot of those. So if we go to the ice caps, ice layers, so you see a lot of water, but that water is not liquid. So the same problem is a desert of life. So you go to the clouds. The problem with the clouds is that the soil there suspended as aerosols. they tend to precipitate, and they cannot hang enough time to create a permanent ecosystem. So it's a transition because, yes, microbial life could be transported to the clouds, and they will have some rest time there, 1 week or so. And but to make a stable system there is not possible because you cannot provide that nutrients in the soil. Ocean surface have the same problem as the clouds. So the soil precipitates. So those essential nutrients like phosphorus and also iron precipitate, making the ocean surface less habitable. It looks like a desert of life. So thinking about life and water, if I see something like that, I will say, well, if life is, it can adapt to anything, why not it adapted to this? I should expect a forest of aquatic plants all over the oceans in the world, but it's not. So animals there, fish and mammals, relies on near the coastal lines just to provide that ingredients and other ingredients provided by the soil, and also the precipitation and transport of dust through the air, just to provide that energy for this life. But it's not as big as compared to the rainforest. And the deep ocean is much worse than everything in terms of light, the energy. You have chemical energy, like for example in hydrothermal system, but not as deep you go in the ocean, then it gets worse. And you don't have so much atmosphere, gases dissolved in the, so it has two problems. So if life is so robust and we have life on Earth and it can adapt to anything, why all type of life was not able to adapt, at least complex life was not able to adapt to all this environment? And the reason is not going in more from biology to physics and chemistry. So there are some hard limits there. And microbial life, as I said, all these places are habitable for microbial life because they need much less resources. But if you want, so this is telling you something very important. If you want planets like Earth, you don't want planets like all these pictures here. You want planets like this, like Earth, able to have forests. So you are asking for a planet with land and oceans, just like Earth. You're asking also for a planet with precipitation. And that's something very important because that precipitation relies on the ocean, a large body of water, to provide that water. And going into a little bit more details, so as I already said, the habitability is defined as the suitability of an environment for life. It is proportional, and now we're going to the biology of the problem, proportional to the carrying capacity of an environment. So this carrying capacity is the maximum stable biomass that can be sustained by an environment. So of the total mass available in those all energy and mass resources of an environment, only a small fraction will be usable by life. And sometimes life will demand more, and it will take for some time more of these resources, sometimes less. But at some point, it will reach one equilibrium with the environment in terms of using these resources. And that's the carrying capacity. So in biology, how we measure, and this is the oversimplification because it gets a lot more complicated, but the general equation for habitability, to put habitability, to quantify, to put a number, is that you select some static condition, which is your environment, some variables that you are interested, and you have to pick a standard of comparison where you know this environment, and you know also these parameters. And when you see this, you say, well, what I can do here is many things. But the restriction here is that no matter the variables that you pick here, you have to make sure they are proportional to the carrying capacity of the system. In other words, to the mass available for life. In this case, for example, the nutrients. Here I'm showing you an example of this application of one model that we are developing. Is a mass energy habitability model. It's an extension, a more general extension of the model used by biologists, so we can apply to astrobiology to consider more wide scenarios. But here is applied to Earth. So any habitability model, you have to test it with your planet first. And here are the images of the environments I showed before. And when we evaluate all the resources, we can make a plot of comparison, which one are better or worse. Better or worse to having a large biomass per unit space, per unit time. And rainforests dominate. So definitely rainforests are the most habitable place on our planet. And then you go to ocean surface, deserts, the ocean, polar desert, and the worst, even that deep ocean, you don't have two, but the worst of all is clouds. Clouds are the worst environment for life. And we were talking a few months ago about life on Venus in the clouds of Venus. That's a stretch. And I think the clouds of Venus are much worse than the clouds of Earth. So, well. So this is the general theory. And now we're going to in detail for how we can apply this for exoplanet, because this general theory could be applied to any scale. If you are studying a microenvironment, studying an extreme environment, if you want to understand a biome or understand the complete biosphere or consider exoplanets, then you still can apply this. So, but first, how astronomers determine if planets are potentially habitable? Well, first step is their orbit. It has a habitable orbit. What we mean here is that the planet orbits within the habitable zone. So this is the region around the star where a planet just Earth-like in terms of atmospheres and size will be able to sustain liquid water at the surface for a long time, like an ocean. If it gets too close to the star, then it will be in the red zone here. It's too hot, and the heat and the energy from the sun will probably erode the atmosphere and also the water there. And the problem is, if it is so far away, then it's too cold and water will collapse as ice. And that's not good either. So this is the sweet region to be the planet, for a planet. So that's the first filter, because it's based on things we can measure. This habitable zone depends on the temperature of the star and the luminosity of the star. So it tells you a box of region of possibility according to simulation of planets. So this relies in simulations. And the next filter is the planet has a habitable size. What we consider habitable size is 0.5 to 2.5 Earth gravity. And that's the radius of the planet. So about Mars size and a lot bigger than Earth, more than 2 times the size of Earth. And that will be probably an ocean planet. There is this upper limit 2.5 is probably still too large, because once you have about 2 times the size of Earth, probably you will have a thick atmosphere. And if your atmosphere of the planet is at least 1% of the total mass of your planet, then the pressure will be over 10,000 bars. And then any water will be liquid, no matter the temperature. So if you are interested more in rocky planets, more like Earth, then that limit could be 0.5 to 1.5. That you will be more certain that the planet is rocky. Now, once you go about 1.5, you take the risk that the planet, it might have too much atmosphere, it will be an ocean planet, so it only will be a mini Neptune, no solid surface at all. So there is a confusion zone there once you go about 1.5. But to include everything as possible, and now we are looking at planets and we have some limits and errors of the size of the planet. So we are sure that if we take 2.5, we are including everything, but we also know that something there might not be as we believe. This, in terms of Mars, it will be 0.1 to 10 Earth masses approximately. So those are the first two criteria, for simple criteria for selecting if one observable planet, because you can measure their orbit, you can measure their size, or at least their mass. So to decide that the planet is potentially habitable, if it has an atmosphere, it might have the condition necessary for life. We also do something in our catalog. We also do some additional metrics, which is called the Earth Similarity Index, or it's a measure of Earth likeness. So this is totally different from searching if it has the right orbit on the habitable side. It's looking at their data of their orbit and size, but comparing directly to Earth. So the index tells how those observable parameters compare to Earth, where Earth is 1, so it will be identical, to 0, to totally different planet. Usually when you see the planets that match your conditions to be habitable by these first two conditions, that translates to about 0.5. So when we do this analysis and we see that the planet has Earth similarity index about 0.5, it will also be in the habitable zone or have the right size, and the closer is better. So this is a totally different metric. And the idea is that this is a different approach, and we use this approach just to sort out the candidates. Once we apply the first two metrics, everyone looks the same, and it's complex to have all that much planets and to see which is closer to terrestrial condition in terms of those measurements. So we apply this and it sorts out the candidates just for illustration purposes. And here we have all these candidates, and we have a catalog of potentially habitable planets that we established in 2011. And at that time, we were in doubt of creating a catalog, but because there were two candidates at that time, and we thought, well, maybe it's not necessary catalog. Maybe it will be hard to detect this Earth-sized planet in the habitable zone. But we decided anyway to do it. And after 1 year, we have 5, 6, and the rest of history. So right now we have up to 60 candidates. But here I'm showing you only 24. 24 which have the radius below 1.5. So these are the ones that are more likely to be rocky. The other ones might be super Earths, ocean world, or even mini Neptunes, and not habitable at all. So these are the best candidates so far that we have. And you can see as comparison Neptune, Jupiter, Earth, and Mars here. And all these pictures, of course, are computer renderings and artistic representation, because as I said, we only have information about the orbit of the planets and the size of the planet. And the problem is here that because we only have that information, we don't know exactly what kind of planets are these. And we can divide the kind of planets regarding their water content. And one way to divide it and categorize the planets, some might be tidally locked planets. And that might happen for the planet here that doesn't have the Kepler signature, a name, because those are mostly around red dwarf stars, which are very common, but the planet has to be very close to the star to get enough energy to keep the water liquid. But at the same time, you will have stronger gravity field that put your planet tidally locked, always facing the same face to the star. So one face of your planet will be overheated, and the other place will be a cold night, trapping as ice any water at all. So, and you might have a transition between these two types of environments. But thinking about what I already said about the requirements for life, if you want planets with forests, you need precipitation. And the problem here is that where is the big ocean to provide that rain? And having here this transition point might not be that big of a water content to provide sustained environment or raining environment there. So I don't think that even that these planets might be the most common, the issue is that I don't think they are that good for complex life, like plants, animal, or even considering intelligent life, but at least good for microbial life. So there could be desert planets, not enough water. These planets are not like tidal locked planets. They're not facing, they're rotating, and their energy is distributed. But they don't have enough water. They might have rivers, lakes that percolate for millions of years through to the lithosphere. And no rain, this is a big desert. Again, something good only for microbial life. Then you have ocean planets, and people get excited with ocean planets. Okay, whales, fish. And the problem is that, okay, you need the land to provide phosphorus and other important ingredients. If you have all the ocean there, the land will be deep below the surface, and that water will dilute more than what happens here on Earth. So the problem is that then you won't have enough mass and energy to keep large animals. And again, microbial life. There's a possibility that some of these tidal locked planets, if they have enough water, it won't be like the water will be circulating and it won't freeze over because the heat from this one will move the water and keep the cycle. But it's still the same issue. Too much water is not good. You cannot live out of water alone. So microbial life can do that because the nutrients will still be dissolved, but not in enough quantity for complex life. And finally, what we want, Earth-like planets with land and oceans. And of these 4 categories, we don't know which category is each of these planets. Even those that are tidally locked might still be rotating, so we cannot be sure that if they're tidally locked or not. But the problem is we don't know what category. They could be even without atmosphere or too much atmosphere. Something totally different, weird. So that points to me that I think these 3 first categories are the most common ones. And to happen that's less likely. So I will bet that this is habitable at all and only good for microbial life. And maybe in the solar neighborhood, we're the lucky ones to have the right amount of water, not too low, not too high, just to keep an ozone level and abate. And we have land areas for creating forests and provide food for animals that eventually evolve to intelligent life. People ask me a lot about water in the solar system, And I always like to show this for comparison. Like, water is not life. Water is just another chemical component, which is there's a lot of that in the universe. So our planet is called Earth, but when you look at the picture, it's so blue that it should be called ocean or something like that. No, that's fine. We should call it Earth because if we put all the water in, it will be a small droplet compared to the size of planet. So average depth of the ocean is 4 kilometers. So it's a small layer of water that we have in our planet. So we believe that Mars had comparable water, at least on the scale. So it has a small ocean, probably half kilometer deep in the northern, long time ago. So that's the water that we have in the terrestrial planets, allowed by the sun, which probably we had at the formation much more water, but then the erosion of the atmosphere and the water, we lost a lot of that water. And Mars definitely lost everything and just remaining the ice cap, or at least we still have water. But if you look at moons in the solar system like Europa and Ganymede and the here to scale, you see that they have a lot more water, because that's natural process of the formation of planetary system. Most of the volatiles, hydrogen, water, they go away once the star goes into fusion and takes those to the outer parts of your solar system. But the problem is that eventually they will be too far to be liquid. And here I'm showing you the part that is liquid. So I am not counting here that you can see that Europa has an ice layer of about 10 kilometers or so is estimated. So below 10 kilometers or so, you have this amount of water, which will be about 100 kilometers deep. For comparison, as I already said, our ocean is 4 kilometers deep in average, and deepest 11 kilometers in the Mariana Trench, but 4 kilometers in average. So here is on average 100 kilometers. That's a lot of water that below that ice layer. The same for Ganymede. And if we look for farther away in the solar system, Titan, well, the moon is farther from the sun. So you should expect more water. Yes, you have a lot of more water. And that water probably is also mixed with ammonia. So that's something interesting. But below that atmosphere, below that crust of mostly ice, which is the rock there, then you have all that water probably mixed with other things like ammonia. And Enceladus, proportionally, it has, which is a small thing here. You can see it here, and proportionally, it has about the same amount of water. So water is very abundant, but if you want animals, you want that water at the surface. You want that water next to continents and not just only water. So you try to apply this habitability general concept. And when I practice this with a lot of my students, and I ask them about Europa, and I tell them that there's a lot of water, ocean, I always ask, well, that should be fish, octopus, and whales, something like that below. But after I teach about only the basics, the habitability conditions using the analogy of the classical elements, and then realize, okay, the energy, wait, that's below 10 kilometers of ice. What gases you have there to provide, for example, nitrogen? You need nitrogen for DNA. You need also oxygen. Well, you might take that from water. But then you will need phosphorus, which will be zinc. Then realize that that's worse than any ocean on Earth. You cannot go worse, so much diluted as any ocean on our planet. So in our planet, we have life. And in those conditions, we have the presence of life very limited. Only microbial life And it's a transient zone for other complex life that relies on other places. But it's not something stable. And we have life. So I think that environment is very bad and probably good for microbial life. So only microbial life in our solar system beyond Earth. So exoplanets are the good alternatives. The other alternative for something else. But there are so many unknowns. So here I'm showing you the solar neighborhood, all the nearby stars. You see that most of those stars are red because red dwarf stars are the most common stars, 75%. And you see a few of the other stars, yellow stars, and which is, we call G star, F stars, which is a little bit bigger and hotter, or K star, which are orange stars, a little bit smaller than our sun. But it's dominated by red dwarf star. So by statistics, so far what we are discovering that these potentially habitable planets, at least that they match the criteria of the habitable zone and size. So if we translate that to the nearby stars, so we might expect about 160 or so potentially habitable planets there. Again, these are the closest system to us, so that's a lot. But again, they're mostly about red dwarf stars. And that tells me that they might be tidally locked, and there's so many other issues with these stars. And there's a few sun-like stars, and planets are maybe mostly like desert ocean planets. So we might be the only terrestrial, right at the center, terrestrial planet, which can have a large biosphere. But if we got further, considering this statistic for the whole galaxy, we might be having over 50 billion potentially habitable planets. So population in our planet today is about 7 billion. So there are planets to give to all the people of Earth right now, those that already died and those that are already coming in the future. But the problem is that they are too far. The same if we consider the rest of the galaxies in the universe, so probably 5 trillion. So we can forget about all the 5 trillion potentially habitable planets in the universe. We can forget about the 50 billion in our galaxy. Only the ones nearby, we will be able to tell something more that stay saying, well, that's potentially habitable. I don't want that. I just want to know if it's habitable or not. I just want to know what category they are. If they are ocean planets or desert planet, tidally locked, or terrestrial planet. I want to know. So only of the nearbys, you will be able to do that. We are discovering planets farther away, but that's it. We know that they are there, but nothing else. Only the nearby ones we will be able to tell something more. And this is a summary of the future exploration of the habitable worlds. So today we know the orbit and size, and that's why we say potential habitable. So that's what we have been doing in the last 10 years. Since 2010, we have been discovering these small Earth-sized planets in the habitable zone. So only 10 years. And we have been saying that they are potentially habitable because we know the orbit and size, but we want more. And in this decade, we will know something more about the atmosphere. We already started. One of the planets in our catalog, K218b, was the first in 2019 we were able through Hubble to learn something about the atmosphere and say maybe it has some water, but this planet is quite big, probably 2.5 already. And that's the transition point between super Earth, mini Neptune. So definitely it's not Earth-like, but at least we are starting to see the water in smaller planets. And so in this decade, we will know about the water, CO2, and probably O2. James Webb Space Telescope will be launched later this year. Will be able, probably definitely, to detect CO2, methane. It will be hard for it to detect O2, water, that's fine, and other components. And once we detect these components in the atmosphere of this planet, we'll say, aha, now we know it has atmosphere. Now we can say, well, likely habitable. Good. But we want more. We want to know, is this a terrestrial planet? And for that, you need to know something about the surface. And probably that would take 20 years or more. And that's knowing that it has the ocean to land fraction. And you will say, how we will know that? If we look for, there are different types of telescopes we can use that are planned that will be able to see these planets as points of light, just a dot. So how we will get any detail? Well, you don't get that detail, but as the planet rotates, when it's a land area facing you, land areas tend to be lighter, oceans tend to be darker. So if you see through observation through many months or years, you see just changing due to rotation, you can, using a different models, tell that if this is something related to brightness or changes on the natural changes of brightness on the surface, or it's due to ocean length, and even tell the fraction of ocean length. And it has clouds, then it will skew you and it will take longer for you to determine that. If the planet is whole desert, you won't see any difference at all. Is it totally covered with clouds? You won't see it. Is it full ocean? You don't see anything. But those that you don't like, do you want, because not there are that's so air-like, then it will be easy to identify, because only those that are air-like will have a strong signal that tells you. So that's good. So we might know that in 20 years or so. And we want more. We want life. And even that, when exploring the atmosphere, we might be able in between detect oxygen and say, well, that oxygen is probably, there will be always doubt. There will be doubt that oxygen produce some way that is just natural and not related to life. So there will be always doubt. To take that doubts away, you will more direct detection of life, and you will see the spectra, the composition of the light divided by different frequency, which tells you different absorption through different gases. And you will see the green, the absorption of plants. If that planet has continents like Earth and it has a green vegetation, then large enough, then it will be a strong signal of some process related to life, like photosynthesis going on. And so that green will tell you, okay, definitely that planet is not only habitable, but is populated with life, and that will be great. That was always studying something so far away. There will always be doubts about the interpretation of results, but that's the point that we should reach probably 30 years or so with new, bigger telescope on the ground, and especially in space. But people will be asking, let's say that we detect a planet like that. Okay, it has the green of plants everywhere. We only see as a dot, but I want to know more. I want to know, does it has animals? Does those animals evolve to intelligent life? We want to know that. So unfortunately, there's a stop here. We cannot learn more this way. And probably just to know if they have animals or intelligent life, you have to go there. which is probably something that will take us thousands of years, enough in our lifetime. But I want to know more in our lifetime. There's a trick. There's a trick. And here is a close view of Earth. You see the vegetation, you see deserts, clouds, the ocean, very clear. But now let's see that Earth from the nearest star with a big telescope, much bigger than we have already. So as a reference, I'm so sorry for you, Arecibo Observatory. So for reference, here is Arecibo Observatory, and let's say we build a 10 kilometers telescope, optical telescope. It doesn't have to be one piece, especially, actually, it's better not to construct in one piece. So many pieces separated far away. You will have, you need the area because that provides sensitivity to low light, but you need a separation to also provide you resolution. So the best way is to spread that out through the planet. And so we have the 10-kilometer telescope, something huge, like a town. And if you take that telescope and look at our planet, you will see this. Well, that's not much. But as the planet, at least it's not a dot, but as the planet rotates, you will see the green changing, the deserts, the ocean, the clouds. You will start to reconstruct the climate of that planet. Wait, but I'm constructing this to learn more about intelligent life. I want more. Oh, okay. So let's construct a bigger telescope, a 100-kilometer telescope. That's as big as Puerto Rico, like the ceiling of Puerto Rico. So if we construct that and put it in the nearest star, again, it doesn't have to be one piece. This could be constructed parts in Earth, parts in space, in orbit around our sun. And then we look, then you will see something like this. This original image will become this. And that's amazing because now you can even see islands. Yeah, you can even see Puerto Rico somewhere there. You can see so much detail. And these are telescopes that might take. So I was talking about 30 years to know something about probably if those planets are habitable at all. But this big telescope, maybe through the motivation that we find something, maybe they will motivate the planet for constructing the huge, maybe 50 years, 60 years. So we might be still around. At least you, Eli, will be around. So, and this telescope will be observing this body. But wait, I'm losing track here. I am constructing this just to detect intelligent life in the planet, just like us. Not waiting for it to transmit it like the SETI projects are doing. I just want to detect it. But even in the original image, you cannot see that there's intelligence like there. You don't see the cities. It's not enough resolution. Less here. But as this planet rotates and you see the nighttime, you will see the lights of the city telling you, oh, there's some intelligent life here. That during nighttime, you just turn on the lights and you will be able to see that brightness. If you see that the planet in the nighttime is dark, okay, I got the point. It has vegetation, but there's still not in that phase that there is an intelligent life. Maybe if it's an advanced civilization, you will see the cities covered. You will see the gray of the large cities through the whole planet, but that should be a much more advanced planet. So there's this very small possibility that in our lifetime, we'll be able to construct such a huge telescope, and there are other ideas, just to see these details, at least for the nearby ones, just to have pictures like a space probe, and then say for sure, and definitely not only any kind of simple, complex life, but also intelligent life. So I will to grow quickly about something that we are presenting this week. And this is how we construct a habitable model just to try to speculate how good are these planets for any biosphere. So you're establishing upper limit. So the worst case scenario is 0 biosphere, but we want to know how big compared to Earth could manage. So these are complex models, but the basic construction is simple. You just have to select your parameters of interest. So it doesn't need to have you to know all the things about the planet, but at least something basic. And that basic thing that you need for a planet, the most basic thing is the size of the planet. You need that. You need information about the atmosphere, at least the base of the pressure or percent of the atmosphere of the planet, surface pressure, average temperature, and the ocean fraction. These are things that we might be able to 30 years or so telescope we be able to figure out, at least measure directly or model. So that means that we will speculate about how big are these biospheres compared to Earth. So I will skip this one because this is a long one, but we can apply here for one of the famous planetary system. The most famous is 40 years light years away. It has 7 planets, all planets compared to Earth, and you can see Earth here at about the same size, some a little bit bigger or smaller. And according to their mass and size, they must be rocky, but they are around a red dwarf star. So probably these 3, 4, or 5 here are tidally locked to the star facing, but that's not necessarily true. It might happen that they're independently rotating and not tidally locked. We cannot be sure, but probably they're tidally locked. So that's the bad news here. And but at least you might have this DEF and DEF planets are in the habitable zone. And we can apply here different models. First, a model to calculate a surface temperature that we propose in one of our 2017 papers. And we can put, based on general circulation models, numbers to these values of potential temperature, and we can get a range of possible, these red lines here. And here, Earth, for reference, Earth doesn't have a range. That's the 288 Kelvin temperature average globally. So, but these are the possibilities for this planet. So you see the planet could be much hotter than Earth, but also colder than Earth. But that will depend on the type of atmosphere it has, and if it's tidally locked or not. So that's the big uncertainty, because we cannot measure that. But putting these numbers here and use a habitable model, we can do the green thing here. And in this model, for reference, Earth is 1, and you can see that the potentially habitable condition in this planet for a biosphere are much lower anyway than the case of Earth. That means that is telling you that it will be, in practice, what it means that if Earth has certain amount of biosphere, total amount of biomass, these are the fractions of biomass that you will expect in this planet. So because it's lower, it means that they will be harder to detect, because this lower amount of biomass will mean that it will impact less the gases that in the atmosphere, and it will be harder to detect any signal from in the atmosphere. But at least we have something here about this planet, and this is something, and this has a little bit chance compared to Earth. So the idea of this model is that this is one model that uses these parameters here, but the idea is to have different models. It's not like we with doing habitable models consider that that this is the model that tells me is this habitable or not. That's crazy. This model tells you a hint on with respect to the variables that you pick, what you might expect. But then you have to create another model with all the variables, other more details, considerations, which you will be adding more things that you don't know because you're asking for more details, but at least you're exploring the possibilities. And then that model here, you might say that this is more habitable for this kind of light than the other. And you will have then a panorama of all the possibilities down there with respect of different models. And some of the models, it will telling you this is the one, because all are most of the model pointing that they have some potential, no matter how you look at it. And if you look for biosignatures and you find biosignatures in that planets, like you have oxygen, methane, you say, bingo, it matched our predictions. But is it the other planets and not the planets? You say, okay, let's say the biosignature interpretation is correct. Let's say that your habitability model is correct, but your habitability model is based on terrestrial life. Then you will say, oh, this is life as we don't know it. This is something that does not operate as we know that terrestrial life operates. Because these are always these models are based on terrestrial life. And this is an important thing because it is the only way to tell apart if something is related or not to Earth. So that's why important. Of course, with this model, you can speculate and they allow you to put more crazy things. But at some point, your physics and chemistry stop you and say, okay, that's not something that you can go with life and explore wider possibility. But at least you try first with a very terrestrial model. You have to try to first and then go beyond that in the process to have a complete understanding of the system. So in conclusion, these habitable models are essential to characterize habitable environment on Earth and beyond because they help to integrate and quantify the effect of many planetary and stellar variables on life, like those illustrated in this figure by Mendez et al. Habitability is positively correlated with the abundance and diversity of life on Earth, but we don't know if this is true elsewhere. Therefore, any biosignature detection should be complemented with habitability analysis to help in the interpretation and validation. Planet radius, surface temperature, atmospheric pressure, and ocean fraction. These four quantities are an example or a minimum set of planetary properties to start assessing the global habitability. And we only know the radius. So all the other ones are just by modelings and trying to explore the possibilities. This is something we can, but we are trying different models and we can put these variables. And eventually, probably in 10 years, we will have at least surface temperature, atmospheric pressure, depending on the gases we detect in the atmosphere, we can estimate the pressure. And in 30 years, we might see those planets are a dot and measure the ocean fraction. And then establish and then compare that with direct biosignature detection. Okay, so for more information about habitability models, we have not only applied to exoplanets, to any type of environment. We have a white paper, the Cal survey, and here is the reference. And so I am just showing an example for apply for exoplanet. So that's all. Thank you very much for having me. And I am open, totally open for questions.
Awesome. Thank you very much. Yeah, I really enjoyed that. Thank you, Dr. Mendez.
Thank you, yes.
Yeah.
Thank you.
So we can start taking some questions. While you guys are typing out your questions, I'm just here to let you know that if you check the description of this video, you will find a link to a Google form that you can fill out if you want to stay updated on this speaker series. There will be monthly emails sent out if you sign up for reminders and for links for other talks in this series. So if you're interested in that, check the video description. Also in the video description is more information about the Society of Physics students at Marshall University. So if you're a Marshall student and you're interested in joining SPS, you should check that out. Also, if you're interested in donating to Marshall Society of Physics students, we are accepting donations. Right now, we are doing sort of a fundraiser with those donations. If you make a $5 donation, we enter you for a chance to win a River Green 45-quart Yeti cooler. So the weather's starting to warm up today, and reminded me of going camping this past summer. And so a Yeti cooler would be really nice to have at this summer. So if you want to enter for your chance to win a Yeti cooler, you can donate to us. Just check the video description for that link to the SPS webpage. Okay, so taking questions now. I don't see anyone has said anything yet questions-wise, but we have Vuelos Espaciales said to repeat this in Spanish, please. And then Jose Rosada says, okay, what's the range of stars expected to have habitable planets, FGKM?
Okay, so yes, those are the stars that we believe might have potentially habitable planets, F, G, K, and M's. And the most abundant are the as at Endor, the M stars. There's 75% of those stars. The remaining stars are the rest. But the problem with the F stars, which are a little bit bigger, and that's why that's the limit. They don't last long. Our sun can last 10 billion years or so more, but these F stars could last 2 billion years, 3 billion years or less. And that's probably not too much time to at least to create a sizable biosphere, at least a detectable biosphere. So these planets around F stars are doomed to be destroyed quite soon before anything interesting is happening. So that's why there's a limit for those stars. But regarding to G stars, K and S, they live, Endor, for example, they live forever, literally forever. And then they have so much problems, as I said. And some people are more optimistic about Endor stars. Some people are more pessimistic. And so if I had to say the fraction of estimates, so fractions go up to about 50% of stars in total have a potentially habitable planet in those categories. But if you're considering sun-like stars like G or K, that's probably lower, 30%, 10% of those stars might have a potential. And potentially with that habitable submetric and size, and if we consider the categories there, so much less of those might be just Earth-like. So it only means that these planets might be Earth-like planet will be possible because Earth is the proof that planets, there could be habitable planets and with intelligent life. So that's just proof of that. We are not asking for square planets. We are asking for something we already know exists. So don't wonder, oh, we detect a habitable planet. Oh, that's like our planet. But it's just one more example. But that example could be very far away. And I worry that it could be that far away that is technically undetectable. And we are, again, alone in the universe for a different reason.
All right, thank you. Pathbar says, thank you for the great talk. Ellie or Dr. McBride, did you have any questions you wanted to ask?
I do, actually. First of all, thank you. That was really interesting. Really enjoyed it. So I have a question. I'm sure you get this one all the time, but what is your favorite exoplanet?
Oh, wow. Okay. So I go with the community in terms of the system that we might know more in the near future, 2 years, 3 years, the TRAPPIST system. That's a exoplanet laboratory. It's not only that they're Earth-sized in the habitable zone, that there are so many of those in the system, and you have hot planets and cold planets. And that's something very important because you need context for comparison. You will see that those are the nearby planet without atmosphere, and you want to see that, make sure that's what's happening. And that's why it's the best laboratory to know something. But taking that away, I like the nearby ones. I think Proxima Centauri, it has some charming, and the planets we observed from the Arecibo Observatory, Proxima Centauri was not observable from Arecibo, but we observed Barnard Star, which doesn't have a potentially habitable planet, but it has one farther away, a cold planet. We also observed Lightning Star. We also observed other stars, about 2 more with no potentially habitable planet, but just studying the star because we cannot see anything with the planet. So, but Proxima Centauri is I don't know, there's something there, but I mean something fun, but I don't think much about life.
Cool. So I did actually kind of further up in the chat see some comments from Peter. So he is another member of our club. He said, I think early on in the talk, he asked, what about the biosphere in addition to the atmosphere, the hydrosphere, and the lithosphere? I think you did kind of talk about that, but then he also mentioned the magnetosphere. He said the magnetosphere is essential. So I thought that was an interesting thing to bring up.
Yes. And I've seen that question popping a lot by astronomers. Oh, we cannot define habitability. Oh, then the sample of magnetic fields. How can we put that in biological context? And the answer is easy. Well, there's a hard part, but that part is astronomy, it's not biology. Is that what you need? Oh, and I think I got it here because you are seeing still my presentation, right? Yes. Okay, these are the quantities that you specifically need to calculate. Is the fluxes. So if you, for example, take as one of the variables B, the magnetic field of your planet with time, with respect to time, because you want to be the evolution of that, then you will need how that magnetic field changes all the amount of your atmosphere, let's say by protection from the erosion from the, so you have to put a model about the initial quantity of the atmosphere, how much it will protect your hydrosphere. Well, it doesn't do anything for the lithosphere, probably. And how it might change, because this changes the more atmosphere, and it will change also the energy that you deliver to the bottom. So these are just physical questions. This is the hard part. You have to put the models in this quantity. Once you put the models in this quantity, the rest is straightforward. Because the models, what they need is these numbers, the fluxes, with respect to space and time. And then we take, and here is the biology, which we will connect it, which relate some of these variables for what we know, what will be the response curves. Or for example, for temperature, you will have a minimum temperature where things could grow, an optimum temperature. So there's a lot of this response curve for different variables. So you don't need this about the how the life will interact with the magnetic field. Once you have this information, you will use that to get the response curve, which are available already in biology. So that's the construction of the model is quite simple once the hard part are made just to put those variables in terms of these fluxes.
All right, cool. Thank you. So Ellie, Dr. McBride, any other questions from you guys?
I have one more. I apologize. I actually had 1,000, but I'll keep it to one since we've already taken plenty of your time. So I was actually just curious. So you talked about kind of the limitations in terms of being able to look at planets. They need to be fairly close, and there are about 160 stars that are within that range to where it's kind of reasonable to be able to assess that habitability to a somewhat higher detail. So I was just curious, in terms of the current planet searches that are going on, tests and other things, do you think that they are focusing enough on that sample of stars, or do you think that more could be done in that area?
Well, what do you mean? What kind of stars?
Sorry, I guess just, are they searching the 160 closest stars enough, basically? Or do you think that
okay.
On your source?
Okay, so yes, we have to recognize that these searches are based on things that we think we can measure. And that is a big bias. You might think, okay, sun-like stars are the stars to go. But if you take the James Webb Space Telescope and just figure out if you will put a planet there and will be able to detect any biosignature, you won't, because the signature will be strong enough. So even that this might be the best candidate, you are proposing, okay, I want to study the best candidate with this instrument, but my instrument cannot do it. Forget it. Okay, so I have to, okay, I can go through this case that we don't know, maybe worse, but I will know. I am able to detect something. So that's what is moving things like considering not end dwarfs because they are abundant and planets are easy to detect. Consider the classical habitable zone about water, surface water, and people complaining, but what about surface? Because we cannot detect that. Even our solar system relies on probes, and we are not doing that. So that's far away. So we cannot propose something like that. Yes, I know that will be something interesting to know, but we are only limited. So definitely, all our observational bias has to be that way and closer systems, because those are the things, the places we will know something about. But we are missing a lot of places, for sure.
All right, thank you very much, Dr. Mendez. I very much enjoyed your talk. And once again, everyone, if you're interested in staying up to date, check the video description for that form to fill out. So thank you, guys. This was a pleasure. Have a good night and a good week.
Thank you for the invitation. Bye-bye.
Bye-bye.
Thank you.
And